Exercise 15.2 says for each of the following compounds, determine whether or not you would expect its IR spectrum to exhibit some signal to the left of 3,000 wave numbers. 3,000 wave numbers. So, in an IR spectrum, you've got the wave numbers on the x-axis, and that's per centimeter. And then on the y-axis, you'd have percent transmittance, so how much light got through or was transmitted through your sample. If 100% of the light got through, 100% at the top, then you just have a line at the top. If 0% of the light got through, you just have a line at the bottom. Usually what happens is you'll have a line somewhere at the top, and then wherever bonds in a molecule are able to absorb light, you get a dip. And so the dips are sort of like the shadows that the molecule is casting. And that happens when bonds vibrate in one quantum way, and the light that hits them is exactly enough energy to make them vibrate in a new quantum way. Exactly that orange amount of energy. If the energy of the light you shine on them is less than the quantum amount of energy, or more than the quantum amount of energy, it doesn't get absorbed, it just goes through the sample. Remember that the ways that molecules can only move in certain ways, they're not fluid like people who could move in any way. There's only a certain number of ways, and so each way is called a quantized way, because it's only one of a certain number, quant. So the light that you shine on them has to have a certain energy. If that energy is exactly the same as the transition in energy from vibrating in one way to vibrating in another, then the molecule absorbs the light and now vibrates differently, and you get that shadow cast in the spectrum. Okay, so there are different landmarks. Different types of bonds have different amounts of energy between their different quantum ways of vibrating. So for example, a carbon double bonded to an oxygen will have a certain amount of energy between one way of vibrating and another way of vibrating. But a different bond, for example, a bond between oxygen and hydrogen, would have a different amount of energy between one way of vibrating and another quantum way of vibrating. And so it will absorb light that has a different amount of energy. And so you can identify certain bonds based on the energy of light that they absorb. Energy is proportional to the frequency of waves. Think about standing in the ocean. The more frequently the waves hit you, the more energy the water has. And frequency is related to wave numbers. So the bigger the energy gap, the further to the left on the IR spectrum, the shadow will be cast. Okay, so different bonds absorb different amounts of energy. In other words, different frequencies or different wave numbers. Now, this specific question is asking to the left of 3,000 wave numbers, and there are a couple specific bonds that do that. In general, a bond between an sp2 hybridized carbon and a hydrogen, that bond vibrates at around 3,100 wave numbers. A bond between an sp hybridized carbon and a hydrogen vibrates at around 3,300 wave numbers. Remember, an sp2 hybridized carbon usually is a carbon involved in a double bond. An sp hybridized carbon is usually a carbon involved in a triple bond. Okay. So, in order for these molecules to have an absorption, one of those shadow dips, just to the left of 3,000, it needs to have either a carbon in a double bond that has a hydrogen on it, or a carbon in a triple bond that has a hydrogen on it. So that's what we'd be looking for in each of these problems. So in here, you'd see this double bond right there. You have two carbons here. You have a carbon, and here I'll just do this in blue. You have a carbon on the left here. This is a carbon, and you have a carbon on the right there. That's another carbon. Do either of those carbons have a hydrogen on it? Well, the carbon on the left has 1, 2, 3, 4 bonds already drawn. That means there are no hydrogens there. The carbon on the right has 1, 2, 3 bonds drawn. That means there's an invisible fourth implied bond going to a hydrogen. And so it's this bond here, that bond there, that would vibrate around 3,100 wave numbers. So you would expect to see a signal to the left of 3,000 in A. You would expect to see a signal to the left of 3,000 because you have an sp2 hybridized carbon. That's usually a carbon in a double bond that's bonded to hydrogen. Okay, how about this next one? Well, we have our double bond. Let me keep the color scheme. So we have our double bond here, and at either end of that we have two carbons. Oops. Carbon on the left, carbon on the right. And what we're looking for is a hydrogen on either of those sp2 hybridized carbons. So this carbon on the left is bonded to 1, 2, 3, 4 other things. That means there are no invisible hydrogens on that. The carbon on the right is bonded to 1, 2, 3, 4 things. So there are no invisible hydrogens on that. So neither of these sp2 hybridized carbons, carbons in double bonds, neither of those have a bond to hydrogen. And so there will not be an absorption here to the left of 3,000. In order to have an absorption just to the left of 3,000, you would have to have an sp2 carbon to hydrogen or an sp carbon to hydrogen. And we don't have those in this molecule for B. How about C? So we're looking for sp2 or sp hybridized carbons. That's where you have either double or triple bonds. We have a triple bond right here. The two carbons on the end of it will be sp hybridized. Sp hybridized carbons are usually in triple bonds. And so we need to know if either of those sp hybridized carbons have a hydrogen on them. First, the carbon on the left. That carbon has 1, 2, 3, 4 bonds drawn explicitly. That means there are no invisible hydrogens to that carbon. The carbon on the right has 1, 2, 3, 4 bonds drawn to that explicitly. So there are no sp hybridized, there are no hydrogens bonded to that sp hybridized carbon. So nowhere in this molecule do we have an sp2 hybridized carbon to hydrogen or an sp hybridized carbon to hydrogen. And so this molecule will not have an absorption just to the left of 3,000. All right, next one. We're looking for double bonds or triple bonds. That's where we have sp2 and sp hybridized carbons. Our double bond is right here. On either end of that, we have carbons. Because these carbons are involved in a double bond, they are sp2 hybridized. So next we need to know if either of them is bonded to a hydrogen. First, let's think about the carbon at the top. It has 1, 2, 3, 4 bonds drawn explicitly. So it doesn't have any bonds, implicit bonds to hydrogen. How about the carbon on the bottom? It has 1, 2, 3 bonds drawn explicitly. So there's one invisible bond there to a hydrogen. This bond here is between an sp2 hybridized carbon, carbon in a double bond, and a hydrogen. And we saw that when you have an sp2 carbon to hydrogen bond, that bond will absorb waves with a wave number of 3,100. A wave with that related frequency will make this bond here vibrate in its next quantum way. It's just the right energy to make that vibrate in its next quantum way, and so that bond will absorb it. So this molecule will have an absorption just to the left of 3000. How about this next one? Very similar looking molecule. We're looking for sp or sp2 hybridized carbons. That means we're looking for double or triple bonds. We've got a double bond here with 2 carbons on either side. But notice both of these carbons have 4 bonds drawn explicitly around them. And so neither of the carbons has a hydrogen. And so you do, even though they're both sp2 hybridized, neither of them are to hydrogen, and so neither of them will give you that absorption at 3100 wave numbers. So that would not, you would not expect that to have an absorption just to the left of 3000 wave numbers. And for F, first we're looking for sp2 or sp hybridized carbons. Here you can see we're looking for double or triple bonds. We have a triple bond there. That means that we have 2 sp hybridized carbons there. And so we want to know if either of these is bonded to a hydrogen, because if it is, then that bond will absorb light with a wave number of 3300 to be promoted to its next quantum vibration, quantum way of vibrating. Okay, well this carbon on the left has 4 bonds around it already, so no hydrogens are there. The carbon on the right, though, only has 3 bonds drawn in explicitly. That means there's a 4th bond there that's invisible, and those invisible bonds are always to hydrogen. So this carbon, we said, is sp hybridized because it's in this triple bond. And here, it's bonded to hydrogen. This bond is the bond that will absorb at 3300 wave numbers. When light with an energy represented by 3300 wave numbers is shined onto this bond will start vibrating in its next quantum way, and that will absorb the light and cast a shadow, and so you'll get a dip at around 3300 wave numbers in your IR spectrum. And so here, in this molecule, you would expect to have an absorption just to the left of 3000, which is what they were asking about.